Assalamu alaikum. This video inshallah will be the start of tutorial number 5. It will be about Rankine cycle, especially ideal Rankine cycle in this video for chapter 10. Okay, let's start with this question. A steam power plant. So we have a steam. So I can know that I will use tables A4 to A6. Okay. Power plant operates on a simple ideal Rankine cycle. So we have an ideal Rankine cycle. Okay, not actual Rankine cycle. We will not have isotropic efficiency. Between the pressure limits of 3 megapascal and 50 kilopascal. And that is a good point that Rankine cycle operates between two pressure limits. The high pressure limit, which we call it the boiler pressure, and the lowest pressure we call it the condenser pressure. As you can see here, the components for the cycle is that you have a condenser, then a pump, then a boiler, and finally a turbine. The condenser is here, so the pressure, the lower pressure, 50 kilopascal, is this one here. It is 50 kilopascal for the condenser pressure from 1 to 4, or 4 to 1 here, from 4 to 1. It moves like this from 4 to 1, and 3 megapascal is here, 3 megapascal. Okay. 3 megapascal is the boiler pressure, which is equal to B2 and also equal to B3, because the boiler is between B2 and B3. That is a constant pressure line. The constant pressure line in the TS diagram is like this. Okay, it's like this. Okay, it will be like this. Okay, so we have that B2 is equal to B3 and equal to 3 megapascal. And when you have megapascal, convert it to kilopascal, and when you have kilopascal, convert it to megapascal, and because usually you will use both, so multiply by 1000. If you want to convert from megapascal to kilopascal, it will be 3000 kilopascal, and B2 equal to B3. This line is a constant pressure line. Okay, there's a constant pressure line on the TS diagram. For 50 kilopascal, B1 is equal to B4. Okay, the lowest pressure in the cycle, the condenser pressure, is equal to B1 equal to B4 equal to 50 kilopascal. The temperature of the steam at the turbine inlet. Where is the turbine inlet? The turbine inlet is here. The working fluid, which is steam, went to the inlet turbine here at state 3. So the temperature, the temperature of the steam at the turbine inlet is 300 degrees Celsius, is T3. Okay, so we have T3 equal to 300 degrees Celsius. The mass flow rate, so m dot of steam through the cycle, the whole cycle, it is a closed cycle. Okay, there is no anything in or out from the cycle. It is a closed cycle. It starts from 1 and go back again to 1. So the mass flow rate is m dot equal to 35 kilogram per second. Show the cycle on TS diagram with respect to saturation lines. Saturation lines are these lines, this dome. Okay, this line is the saturation or the saturated liquid line until this point, the critical point. Okay, and for the saturation or saturated vapor line is this line. Okay, so any point that on this line, the green line, it is a vapor. Okay, the quality is 1, and any point on the blue line is liquid. Okay, or saturated liquid. So here is the saturated liquid line, and here is the saturated vapor line. So he wants to draw the TS diagram with respect to this saturation line. So if you want from you to draw the dome, this dome, and then draw the cycle, and we already have this cycle. Okay, so you will draw it like this. Okay, because Rankine cycle is usually that stage 4 is a mixture or a a saturated vapor on the green line, or it is a superheated state. Okay, and usually if it is mixture, the quality is above 0.9. Okay, but يعني approximately sometimes in the question you will have 0.8, sometimes you will not have anything like this. Okay, but يعني if you don't know the numbers, you didn't solve yet, so draw it like this. Okay, usually in the Rankine cycle, one of the modifications that we have a superheating. Superheating means that after you reach the saturated vapor, you heat the steam. You heat the steam to a higher temperature. Okay, this is the superheating. The superheating is this region. Okay, this region. You can see this one is the superheating. Okay, and here this one is isotropic compression in the pump, and you can see it is drawn like this with an angle. They only draw it like this because they want it to be clear for you, but the correct drawing is it is isotropic, means S is constant, so S1 is equal to S2. The line should be upward like this. Okay, a straight line to up. So that is but يعني they draw it like this because they want it to be clear. Okay, and why we do these modifications? Because we want to increase the area, and the area enclosed this TS diagram is the Q net, or the net heat exchange during the cycle, and it is equal to W net. So if I increase this the area inside the cycle, I will increase the W net, and this will increase the thermal efficiency. Okay, and we compare it to the Carnot cycle, and we will see during our solving how we did these modifications. Okay. Okay, show that the cycle on TS diagram with respect to saturation lines. Okay, determine in part A the thermal efficiency. Okay, so the thermal efficiency for the Rankine cycle in part A of the cycle, and in part B the work or the net power output. Power means dot, so we have W dot net power, so W net dot. Okay, output means output means the from the cycle, from the power plant. Okay, so let's see what is the equation for thermal efficiency and the power output or net output from the cycle. Okay, and output when they say output doesn't mean only turbine. Okay, the net output means turbine minus the pump. So we will see here the thermal efficiency is equal to W net over Qn, the usual equation for any cycle. Okay, here we have the turbine minus the pump. In the Brighton cycle, we have the compressor instead of the pump. Okay, so we always subtract the work producing device, which is turbine, the work of the turbine, minus the work consuming device, which is the work pump in. Okay, is the work done on the pump, so in the cycle, as you can see here, so it is work in on the pump, and then pump will increase the pressure and compress the liquid. Okay, and it's equal to Q in minus Q out, also because the work net output, we said that Q net, the net heat exchange, is equal to the work net output. The area inside the TS diagram is equal to the area inside the PV diagram. Okay, then 1 minus Q out over Qn, and finally 1 minus H4 minus H1 over H3 minus H2. And this indicates that when he asks you about the thermal efficiency, you must find every enthalpy at each state. So we have only 4 states. Okay, so you need to find the enthalpies at each state. So directly you think that let's find everything, find all the enthalpies if he asks you about the thermal efficiency. And also if he asks you it was in second part B, the work net output. Okay, he said the work the power output, so it's W dot. Okay, so instead of this equation like this, we will put dot. Okay, so work turbine dot minus work pump dot. Okay, and it is equal to, we have the mass flow rate given in the question. Okay, we have the mass flow rate given in the question, so we can multiply each one of them by the m dot and get this one. And also we can get this one if I the work.net power output from here, because if I have m dot and I have work.net output from this equation, I can multiply them and get the power. Okay, so also the power needs to find all enthalpies H3 4 2 1. So we need all of this enthalpies, and I think in the midterm also you will solve for all enthalpies. Okay, so we want to know how to get all enthalpies for each state. Okay, so let's see the procedure of solving for ideal Rankine cycle. In the question, he may give you the pressure or a temperatures. Okay, if he gave you the pressure, you will solve with the blue everywhere. I put blue and green. Okay, here in the question he gave me the pressure. We will solve question when he gave me the pressure like this and when he gave me the temperatures. Okay, here we have that he gave me the pressures P1 equal to P4. So at P1 equal to P4, V1 will equal Vf and H1 equal to Hf. Why we are doing this? We assume that for Rankine cycle, always state 1 is at the saturated liquid line. Okay, it is always at the saturated liquid line. Why we did this? Because we are comparing to the Carnot cycle. Carnot cycle, if we draw it on the TS diagram, okay, TS diagram, and I have the dome. Carnot cycle is like this. Isothermal heat addition. I have this one. Okay, and because my drawing is so bad. Okay, this one is isotropic. Okay, so you have isotropic expansion in the turbine like this, and you have isotropic compression in the pump like this. But here you have isothermal heat addition and isothermal heat rejection. Okay, the problem is here in the pump. The pump will be affected or be damaged if you have vapor. Okay, this one at this point is at the saturated liquid line, but this point is a mixture, so you have some vapor. Okay, this will affect the pump. So to avoid this, we because Carnot cycle is not practical cycle, we need a cycle that is practical in real life. So we cannot let this state to be a mixture or be have some vapor. So we move it to be here. Okay, that is why always in Rankine cycle you will find that the state 1 is at the saturation liquid line, and if it is not like this, if it is not at the saturation liquid line, he will say for you a sentence that will clarify where is the point 1, because sometimes they subcooled the state to be here. Okay, why they subcool the state? Because it is better for them, because if you subcool the state at the same pressure 50 kilopascal like this, okay, and then you go up to state 2, okay, you will have, and go again like this, you will have additional area here. Okay, if this is the previous 1 2, okay, and this is the area for 1 2 and the whole cycle. Okay, we will have additional area if I go from to subcool, from saturated liquid to subcooled liquid. This additional area will increase the work net or the Q net, which is equal to work net, and then it will increase the thermal efficiency. So that is why they sometimes subcooled the state. Okay, but here we have it at state 1 here as saturated liquid. That is why I said that V1 is always will equal to Vf and H1 is always will equal to Hf. From table A5, because I have the pressure and the pressure for the steam is table A5. Okay, if it is R1 3A refrigerant, you will find it from table A11 to A13, and for the pressure table for R1 3A it will be table A12. Okay, here we have steam, we have water. Okay, so the first thing is to find V1 equal to Vf and H1 equal to Hf. Why I'm doing this? Why V? Okay, we know that H1 is needed because the equations contain H1, but for V I want to find it because I needed to find H2, okay? H2 is from this equation already, that the work pump in, which is here, okay, from 1 to 2 at this between these two states at this process, is equal to H2 minus H1, okay, and is also equal to V1 B2 minus P1, okay. And this equation, and you don't need to know from where it comes, but if you want to know, you can go to table to chapter, the entropy chapter, I think, and there is equation that the work reversible, okay, because this processes, all of these processes are internally reversible processes, okay. So the work is reversible or internally reversible for pump and turbine for the ideal Rankine cycle, and is equal to negative V dB, okay. Uh, the water here from 1 to 2 is water. It is incompressible substance, so the change in volume is not that huge, okay. So we will assume that the volume is constant, so the volume will go out of the integral and it will be like this, and it will be from pressure 1 to 2. So if I integrate this one, it will be negative V delta V, okay. And the negative, I will put it in the other direction, so it will be negative W reversible, and I will assume that this one is okay, this one is P2 minus P1, okay, of course, because 2 minus 1 in the integration. I will assume that the negative work reversible is the work N, because negative because it means it is N, and it is on the pump, okay. So this will give me, and this one is V1 equal to V2, so I will use only V1, okay, there is no change, it is constant, okay. So V1 P2 minus P1, okay, because we don't have anything to find H2, we don't have, they will not give you T2, they will not give you anything about this, so the only choice to solve H2 is to arrange this equation and find H2 equal to H1, that we will find here, which is equal to HF, and then we add this term which is equal to the work pump in, okay. So the work pump in plus H1 will give you H2. So that is how we can get H2. So let's solve here. Let's go to the table and find V1 and H1, and then find H2. Then we will see how we can get H3 and H4. Okay, so let's go to the table at B1 equal to B4, which is the condenser pressure 50 kilopascal. So I will go to the table, table A5, the pressure table, 50 kilopascal. Okay, 50 kilopascal, and I want to find V1. This one is V1, which is equal to Vf as the saturated liquid specific volume, and also H1 will equal to Hf. Okay, so let's write. So I have at B1 equal to B4, which is equal to 50 kilopascal. Okay, I have that V1 equal to Vf and equal to 0.001030 meter cubed per kilogram, and then H1 is equal to Hf and equal to 340.54 kilojoule per kilogram. Okay, I found H1 and V1. Now I can use this equation to find H2. Okay, so H2 is equal to H1 plus V1 P2 minus P1. Okay, and let's find V1 P2 minus P1, which is equal to work pump in. So let's find first work pump in. You can substitute directly in this equation, but let's find also work pump net, work pump in, because I think we need it here if you want to find W dot net. Okay, so it is also equal to V1 P2 minus P1. Okay, V1 is what? V1 is 0.001030. B2, which is equal to B3, and it is the boiler pressure, is equal to 3000 kilopascal, and you put it in kilopascal because you want the answer to be in kilojoule per kilogram. Don't use the 3 megapascal. Okay, so it is 3000 minus P1, which is 50 kilopascal. This will give you that the work pump in is equal to 3.04 kilojoule per kilogram. Okay, so to find H2, we will use this equation. So H2 is equal to H1. We got H1 to be 340.54 plus V1 0. Okay, why V1 and this thing? We already calculated V1 B2 minus B1, which is 4 pump in, so 3.04. And this will give us that H2 is equal to 343.58 kilojoule per kilogram. And as you can see that the work pump in is very small, not a big number, and this will help you if you want to know your answers are correct or no. Okay, and as you can see also H2 is a little bit higher than H1. H1 is 340, H2 is 343. Okay, because this, as you can see, work pump in is this small, this part, but the work turbine out is all this difference between the enthalpies H3 and H4. Okay, so let's go and find H3. H3 is usually superheated because that's what we assumed, and when we draw the TS diagram, this one, that we have a superheating here from the saturated vapor to state 3, or it is a saturated vapor. They didn't do superheating. Okay, they just put it like here and the saturated liquid saturated vapor line. Okay, but it is better that we have superheating, because if I didn't do superheating, the area will be like this. I will go down from this one will be 3 and this one will be 4, and I will lose all this area. Okay, this area come from the superheating, and by decreasing this area and if I don't have it, if I didn't do the superheating, I will lose the area, and the area means work net, and work net means thermal efficiency will decrease. Okay, because the work net decreased. Okay, so I can find this one at P2 equal to P3 because I have it. Okay, it is given in the question P2 equal to P3. So how can I know if it is superheated or saturated vapor? In the question, he didn't mention anything about saturated vapor, or he didn't mention that he didn't superheat the steam. So I am predicting that it is superheating, but I have to check. Okay, because sometimes they say Rankine cycle, and you will figure out that after you solve that it is a mixture. Okay, it is not even superheated or saturated vapor, but the usual thing it is superheated or saturated vapor. So we are predicting it is superheated. So let's see how can we find it is superheating. If it is saturated vapor, so خلاص H3 is equal to Hg, and you will find also S3 equal to Sg. Why entropy? Specifically, why I choose entropy to write it here? Because in the ideal Rankine cycle, we have isotropic expansion. Okay, and S3 is equal to S4. So I need to find S3, so I can say that I have a property at state 4, which is entropy. Okay, and use entropy with the pressure at state 4, which is 50 kilopascal, to find other things, because in the tables, the steam tables, we always need two properties, so we can find other properties. Okay, so that is why, of course, at B2 equal to B3, because we have it, and saturated vapor means that X3 it is equal to 1, because it is at the saturated vapor line. Okay, if state 3 is superheated, and how can I know what is the meaning of this sentence? I have to check, and this checking is from table A5, because now I have the pressure. Okay, and check if my temperature at state 3 is it equal? Is it higher than Tsat? If it is higher, then it is superheated. Okay, that is the meaning of if state 3 is superheated. Okay, and we will see in a minute. Okay, then T3 or other property at state 3 must be given, and as you can see, we are given T3. If we are not given T3, he must give me another property at state 3. Okay, beside the pressure. Okay, and here I don't have green in this sentence. I will say later when we have when he gave me in the question temperature, not pressure. Okay, to find H3 and S3 or any other property from superheated table A6. So let's check. Okay, let's check if my state 3 is superheated or no. Okay, I will go at B2 equal to B3, and why B2 equal to B3, not B1 equal to B4? Because I am searching for H3, right? Okay, so H3 is related to B3, which is equal to 3000 kilopascal. Okay, and let's check which is higher, T3 or Tsat. So at table A5, 3000 kilopascal is here. Tsat is 233.85 and T3 given in the question is 300. So that means that T3 is higher than Tsat, so it is a superheated state. So let's write this, that T3 is higher than Tsat, the saturation temperature, and 300 degrees Celsius is higher than 233.85 degrees Celsius, so it is a superheated state. Okay. So I will go to table A6. A6 is the superheating table, superheated table. So let's go to table A6. Table A6 with 3 megapascal. 3 megapascal is 3000 kilopascal. Okay, so 3 megapascal at 300 degrees Celsius. So this row. And I want to find what? H and S. We said we want S because it is isotropic expansion in the ideal cycle, ideal Rankine cycle. So I need these two numbers, H3 and S3. Okay, so H3 from table A6, table A6. I will now I'm now using table A6. So H3 is equal to 2994.3 kilojoule per kilogram. And S3 is equal to 6.5412 kilojoule per kilogram, and this one will equal to S4, right? Okay, as you can see that S3 is equal to S4, the same number. Okay, same number. S3 is equal to S4. Okay, so I will benefit from this relation in the next step when we want to find H4. Okay, to find H4, it depends. If my H4 is less than or يعني if the point is here before the saturation or saturated vapor line, if the steam or if working fluid is a mixture, okay, means that X or the quality at 4 is less than 1. Okay, of course it is higher than 0 يعني. I will use this equation, and this equation I need in this equation, the famous equation for the quality, I need X4, and X4 I cannot find it unless I have all the other properties, other property at state 4, which is the entropy. So that's why I said that S3 is equal to S4. Then I can use this equation to find X4, and from this I can use this equation to find H4. Of course, at which pressure? At P4 equal to P1, because you are calculating for state 4, so we will use pressure 4. Okay, and if the quality is equal to 1, and this rarely happen because usually the calculation will not give you 1, okay, then H4 is equal to Hg. But if the quality is higher than 1, and I think this came in the question, in one of the question before in final one of the final exams, okay, that the quality is higher than 1, that means that there is no quality already. It means that it is a superheated state. It's here, okay, it is here, not inside the dome. Okay, so you will use table A6 at the pressure B4 equal to B1, and I will say why. Let's say it here because the okay, you will not understand here. When we go to the next question, we will see why there is no green in this line. Okay, I need to find the quality. So I have S4, SF and SFG can be found at the pressure from table A5. So let's write this equation and find X4. So X4 is equal to S4 minus SF over SFG. SFG means SG minus SF. You can write it like this: S4 minus SF, SG minus SF. But in the table we have a column for SFG, so that's why we will use it directly from here. Okay, at which pressure X4 state 4 means at pressure B4 equal to B1, which is equal to 50 kilopascal. Okay, so I have S4, which is equal to S3. I need to find SF, SFG from the table. They are in the table A5. Okay, at 50 kilopascal B4. Okay, that is the value for SF, this one. Okay, and SFG, this one. Okay, so let's substitute in this equation. So X4 is equal to S4 6.5412 minus SF 1.0912. This 1 minute. This one at 40. Okay, so you'll take this row. Okay, this one 1.0912 and 6.5019. Okay, at 50 kilopascal. Okay, SFG is 6.5019, and this will give you 0.8382. So the quality X4 is less than 1, so it is a mixture. Okay, a mixture between so it is a mixture. It is inside the dome. You have some liquid and some vapor. So you will use this equation, H4 equal to HF plus X4 HFG, and also the pressure B4 and B1. HF and HFG is like SF and SFG. You will get them from table A5. So let's write this equation also, that H4 is equal to HF plus X4 HFG, at which pressure? State 4 H4. So at B4 equal to B1 equal to 50 kilopascal. Okay, the condenser pressure. Okay, so HF is 340.54 and HFG is 2304.7. Okay, so H4 is equal to HF 340.54 plus X4 0.8382 times HFG 2304.7, and this will give us that H4 is equal to 2272.3 kilojoule per kilogram. Okay, so now I found all enthalpies for every state. So let's find the thermal efficiency using this equation: H4 minus H1 over H3 minus H2. So thermal efficiency for Rankine cycle, the ideal Rankine cycle, is 1 minus H4 minus H1 over H3 minus H2, and this will give us that 1 minus 2272.3, which is H4, minus H1. At the beginning it was 340.54, and as you can see here in this equation, HF is 340.54 and H1 is 340.54, and usually you will see it again. HF is the same, is equal to H1. Okay, unless you have subcooling, that will be a different. But to make to have a guess or an indication that your solution is right, that HF is equal to H1. Okay, when you don't have subcooling, when state 1 is at saturated liquid. Okay, so over H3 is 2994.3 minus 343.58, and as you can see, H2 is a little bit higher than H1, or have a value a little bit bigger than H1. Okay, and H3 should always be the highest because it has has a higher temperature. The state that has a higher temperature will have a higher enthalpy. Okay, so thermal efficiency is equal to 0.271 and it's equal to 27.1%. Okay, what about the power? The second part was about the power W net. I have the mass flow rate given in the question, so I will use this equation. Okay, mass flow rate is equal to W dot net power over W net. And if it was the opposite, that he gave you in the question W net, the W net, and he asked about the mass flow rate, you will use also the same equation. And that's what you will see here in this question, in question 1016, that he asked the quality, and we calculate the quality, the thermal efficiency, and we calculated the thermal efficiency, and then he asked the mass flow rate and give you in the question W net, the power. Okay, so no need to solve 1016 because it is the same like 1012, but in the actual cycle we will solve this question, but we'll use question 1017 because it says that repeat problem 1016, assuming isentropic efficiency for turbine and pump. That is the meaning of the actual cycle when you have in the question isentropic efficiency. Okay, so let's stand back and use this equation. This equation requires that we calculate the W net output, okay? And the W net output is W turbine out minus W pump in, or Qn minus Q out. The Q net in the TS diagram is equal to W net in the PV diagram. So you are free to use any of these equations, okay? Either you use turbine mass pump or Qn mass Q out. I will solve with both equations and see that they will give me the same answer at the end. Okay, so let's find first the work net in kilojoule per kilogram, the small one, the small w. So W net is equal to the work turbine, sometimes equal to WT in this turbine, so minus work pump in, okay, equal to Qn minus Q out. So let's solve first with this equation. We already found work pump in at the beginning, but for work turbine out, so let's find work turbine out. So work turbine out is equal to, as you can see from the equation sheet, is equal to H3 minus H4. And you always follow this procedure, that the up minus the down and the right minus the left. So up minus down, so 3 minus 2, 3 minus 4 will give you the turbine out. Okay, 2 minus 1 will give you the work pump in, H2 minus H1. Right minus left, so 3 minus 2 will give you that Qn is H3 minus H2. 4 minus 1, right minus left, will give you Q out equal to H4 minus H1. Okay, so if you don't remember, if you know that TS diagram, if you forgot to write this equation sheet or this equation, you can know how you can get the equation for the enthalpies or the turbine, the work. Okay, so the work turbine out is equal to H3 minus H4. Okay, H3 is 2994.3 minus H4 2272.3. So the work turbine out will equal to 722 kilojoule per kilogram. Okay, and you can find the work net because you have the work turbine and we calculated the work pump. It will be 722 minus work pump was 3.04, and this will give you 718.96 kilojoule per kilogram. Okay, what about if we solve using this equation? Qn is equal to H3 minus H2, the right minus the left. Okay, so H3 is 2994.3 minus H2 343.58, and this will give you that Qn is equal to 2650.72 kilojoule per kilogram. For Q out, H4 minus H1 will give you 2272.3 minus 340.54, and this will give me that Q out is equal to 1931.76. And as you can see, the highest value between W turbine, pump, Qn, and Q out is Qn. Qn, look from where to where? From here, from 2 to 3, all this region. Okay, so it is the highest number, and this will give you an indication if your solution is right or no. Okay, and then if you calculated the W net using the equation that Qn minus Q out equal to W net, this equation, okay, will give me that 2650.72 minus 1931.76 will give that also W net is equal to the same number, 718.96 kilojoule per kilogram, the same number from the previous equation. Okay, finally I can say that the W net, what is required for me in the question, W dot net output is equal to M dot times W net. M dot given in the question is 35 times W net 718.96, and this will give you that W dot net is equal to 25.16 times 10 to the power 3 kilowatt, or 25.16. If he asks you in the question, write it in the megawatt, because sometimes he asks not as you want. Okay, this is 10 power 3 and this 10 power 3, so together are mega. So I will remove 10 power 3 and K and get megawatt. Okay, that is for this question. Let's move to the another question. It is refrigerant. Now it is refrigerant. As you can see that I wrote here A5. I think I will change it to include also the T12 if it is refrigerant. But let's see. Refrigerant. We have refrigerant R134A is used as the working fluid in simple ideal Rankine cycle. Okay, so it is the working fluid. We don't have steam, so we'll use the table from where table A11 to table A13. Okay, we have ideal Rankine cycle. It is not actual. We will not have isotropic efficiency, which operates the boiler. Okay, the boiler means the boiler pressure. Okay, which operates the boiler at 2000 kilopascal. So the boiler is from 2 to 3, or here 2 to 3. That is the boiler. So P2, that's a constant pressure line. Okay, this line is constant pressure line, 2 to 3. Okay, so P2 equal to P3 equal to 2000 kilopascal. Okay, and the condenser, and this one is equal to megapascal, and the condenser is at 24 degrees Celsius. So T4, which is equal to T1, is equal to 24 degrees Celsius. Okay, as you can see here, that the condenser operates between 4 and 1, operates at the same temperature, T4 equal to T1 equal to this temperature, which is equal to Tsat, the saturation temperature, because as you can see, this temperature is on the inside the dome. Okay, it is isothermal, or from 1 to 4, or from 4 to 1. So it is the saturation temperature also. Okay, so at this saturation temperature, we can get also the pressure. If he didn't give me the pressure, I can also get the temperature. If he didn't give me the pressure, I can get the pressure from that I know that saturation temperature. So this one is also equals the saturation temperature. Okay, Tsat, saturation temperature. So I have 24 degrees Celsius given the question. I don't have the pressure P1 equal to P4 as the previous question. Okay, the mixture. So he said for me it is a mixture. It is not superheated. Okay, it is a mixture at the exit of the turbine. Exit of the turbine is here at state 4. Okay, so here it is a mixture. So this TS diagram is right. Okay, it is not here at the saturated vapor line, or it is not superheated. It is a mixture inside the dome. So it is a mixture and has a quality of 93%. 93% means 93 over 100, which is equal to 0.93. So X, which X4, because at state 4, the exit of the turbine, outlet of the turbine, is equal to X4 equal to 0.93. Determine the turbine inlet temperature, T3. So the inlet temperature is at state 3. he wants to find this temperature T3. Okay. Okay, okay, and the thermal efficiency of the cycle, and we say when he asks about thermal efficiency means every enthalpy during the cycle and inside the cycle. So H1, H2, H3, H4, you want to find every enthalpy at each state. And the backwork ratio, as we saw in the Brighton cycle, was the work producing device, the work consuming device over the work producing device. Okay, the work consuming device is the work pump in. You consume work so you can operate or make the pump work, so it can increase the pressure and compress the working fluid, and you produce work from the turbine. So the back work ratio, RPW, is equal to what? Is equal to work pump in. Okay, in Brighton cycle we have a compressor instead of the pump, and over the work turbine out. Okay, that is the back work ratio. And here is the equation for the back work ratio. The back work ratio is work pump in over work turbine out, and as you can see, you need the work pump in is H2 minus H1, and this one is H3 minus H4. So also you need to find every enthalpy. Okay, that's it. Okay, so I need to find the back work ratio. Okay, so let's see how can we find the enthalpies. In this question, we are given the temperature, not the pressure. We don't have P1 over P4, so I will not use the blue one. I will use the green one, T1 equal to T4, and at T1 equal to T4, V1 also will equal to Vf, and H1 will equal to Hf. The new thing that also B1 equal to V4 is equal to B set, because this one and they are on the same line, T set and B set. So this one is B set also if I want the pressure, and the constant pressure lines in the TS diagram is like this. Okay, so all of this have the value for B set. Okay, so and B set, it is equal to the pressure B14. Okay, this line is represents the pressure B1, and which is equal to B4. They are in the same constant pressure line. The line passes through 1 and 4, and it's also equal to B set. Okay, because it is inside the dome we have the saturation pressure also. So I can get all of these V, H, and B from table A4 this time. Okay, and now that's the problem. The refrigerant A4, instead of A4 we have A11, and instead of A5 we have what? A12. Okay, so don't need this one, so we have A11 in the refrigerant. We will change this one. Okay, okay, and then find these things. So let's find them, and then we will use this equation. B2 minus B1. B1 is the B set or B4. Okay, and B2 is given in the question. V1 we will calculate it here. H1 also we will calculate it here. Then we can find H2. So let's find these three things from table A11. So we'll go to table A11 because it is the temperature table for the refrigerant temperature table. Okay, at A11 with a temperature of what? 24 degrees Celsius. Okay, at 24 degrees Celsius, it is given the question T1 equal to T4 equal to T set. We will find Vf and Hf, and this pressure P set is the one that is equal to B1 is equal to B4. Okay, so let's write that at T1, which is equal to T4, which is equal to 24 degrees Celsius, and it is also the T saturation. Okay, and it will not be T1 will not equal to T saturation if there is a subcooling. Okay, because subcooling means that you move down along the pressure constant pressure line and be here like this under the saturation temperature. Okay, means and state 1 will be here. Okay, but now in this question we have it here. We will see a question about this. Okay, it was a question that came in the midterm exam before. T set, okay, and we find that V1 equal to Vf. I want to find V1 equal to Vf at this temperature, 24 degrees Celsius. Also, we want to find that H1 equal to Hf. at this temperature, 24 degrees Celsius. Also B set at the saturation temperature, which is 24 degrees Celsius. We will have B1, which is equal also to B4. So from the table, from the thermodynamics table, B sat, VF, and HF, this numbers we will write them. Okay, so VF is what? 0.00030 zeros. يعني be careful, sometimes you write 2 zeros and you will get the wrong number. Okay, 8261 meter cubed per kilogram. H1 is equal to HF and equal to 84.98 kilojoule per kilogram. B set is what? 646.18 kilopascal. Now I found H1, so let's find H2. H2 is equal to H1 plus V1 P2 minus P1. Okay. So H1 is what? H1 is 84.98 plus V1 0.000861. B2 given in the question, B2 is 2000 kilopascal. So 2000 kilopascal minus P1. P1 is 646.18, and this will give us that H2 is equal to 86.1 kilojoule per kilogram. And as you can see, there is a small difference between H1 and H2. That means that the work pump in is very small, okay, and that's good for us. Yeah, it's a consuming device, work consuming device. So if you want to find the work pump in, because we needed to calculate the backwork ratio, okay, the work pump in is only this term, okay, which is equal to V1 B2 minus P1. Okay, V1 is what? V1 is 0.000861 times 2000 minus 646.18, and this will give you that work pump in is equal to 1.118 kilojoule per kilogram. Okay. Let's find H3. H3, he didn't say anything about saturated vapor, so I will ignore this one. So let's see if it is superheated or not. Okay, let's check. Okay, if state is 3 is superheated or not, so we can see. So I will go to table A12. Why A12? Because it is the pressure table for the refrigerant A12. So here, instead of table A5, table A12 for refrigerant. So don't confuse between these two, or use the wrong table. I made this mistake in the midterm. Okay, this one is table A13 and the exergy question. This one also is table A6. No, this one is table this one is table A11. Okay, this one is table A11. So this one is table A16. Okay, and A13, and I will check in the table, in table A12, the pressure table. Okay, table A12. Okay, I will go to table A12. At which pressure I want to find what? H3. So I will use which pressure? B3 equal to B2. This one, 2000 kilopascal. Okay, so I will go to table A12, pressure table, 3000 kilopascal, 2000 kilopascal. Here the temperature is 67.45. Okay, that is the problem, that already how can I compare? And one of the requirements for me is T3. Okay, I don't have T3, so that is the problem, that I don't have T3. And I cannot compare, and I cannot know what is the state, if it's superheated, mixture, saturated vapor, or what. So if you don't know, okay, يعني اسحب عليه and go to find state 4, H4. Okay, So we'll ignore state 3 and we'll go to state 4 and find H4, because what else we know about state 4? Okay, do I know anything about state 4? So I don't have S4, right? So because S4 is from S3, so how can I find anything about state 4? Do I have anything about state 4? I have the saturation temperature, or T4 equal to T1, and I also calculated B1 equal to B4. Do not use P1 equal to P4, because as you can see, it is not usual number 646.18, so you will not find it. Okay, it will be between these two numbers, and you will need to do interpolations. It will be a long question. So if the temperature is given in the question, use the temperature. Okay, T4 equal to T1 equal to T set. Okay, so what you will do that you need to find the S4. Because you are given the quality. Okay, that is the different here. And the previous question, we needed to find the quality, but here the quality is given, so that is our solution. That the quality, we can use the quality to find S4. So I will use this equation, okay, to find S4, and rearrange it to find S4. I have the quality this time. I want to find S4, and then I will say that S4 equal to S3, and then use S3 with the temperature. With the pressure at B3 and B2, I have the pressure at B2 and B3 to find H3 and check. Okay, so let's use this equation to find S4. Okay, I have the quality, so I can check now. So X4 is equal to SF S4 minus SF over SFG. Okay, so I want to find S4. S4 will equal to SF plus X4 SFG. Okay, at state this one is at state 4, so I am searching for SF and SFG at pressure P4 equal to P1. But we said this will give you interpolation, because if you go to table the pressure A12 table, the pressure B4 equal to B1, which is 680 what is 640 something. Okay, you will not find HF, SF and SFG. You will need to make interpolation. So why you bother yourself with the pressure? Okay, so we'll not use the pressure. Okay, we'll go and use the temperature. Temperature is given T1 equal to T4, which is equal to T set 24 degrees Celsius. So at table what? Table A11, the temperature table. Okay, so we'll go here to table A11, 24 degrees Celsius. Okay, and find that SF is 0.31958 and SFG is 0.6013. Okay, so SF is 0.31958, X4 is given the question 0.93, and SFG is 0.60130. So S4 is equal to 0.8788 kilojoule per kilogram Kelvin. Okay, don't forget the Kelvin, it is entropy. Okay, then after I found S4, I can find already H4 before going back and searching for H3. I can find H4 using this equation. I already know it is X4 is less than 1, it is 0.93. So I will use this equation to find H4 also at where I don't have the pressure, right? I already calculated the pressure with the saturation pressure, but I will not use it because it is we will have a lot of interpolation. And this one, of course, this one was table A11 for the refrigerant, and this one also is table A11. Okay, so we'll use table A11 and find H4. Okay, so H4 is equal to HF plus X4 HFG. Okay, so H4 Of course, I will find this at T1 equal to T4 equal to Tsat and equal to 24 degrees Celsius. Okay, so I will go to the table at 24 degrees Celsius. I want to find HF, okay, and also HFG. So these numbers, HF is what? HF is 84.98 plus X4 0.93. And as you can see, HF 84.98, it is the same like H1, okay? Because we both of them we calculated the saturation temperature. So this will give you an indication that your solution is right or no, or you took the right number from the table or no. Okay, HFG is 178.69. Okay, so H4 will be equal to 251.16 kilojoule per kilogram. Okay, then I will say that I already found everything, but I didn't find H3. So the problem is that we didn't have T3. It was one of the requirements in the question. Okay, so S4, this one is already equal to S3 because it is isotropic expansion process, and we have ideal cycle. Okay, we don't have isotropic efficiency. We have isotropic process, means there is no Q in or Q out, and the entropy is constant in internal reversible process. Okay, so S3 equal to S4. That's why we said S3 equal to S4. Then using S3, okay, with the pressure P2 and S3, okay, as you can see here, then T3 or other property, here we don't have T3, so we have the other property, which is S3, must be given, or you can calculate it, okay, beside the value of P2 equal to B3. So I will change this, not only given, you can calculate it. The one given was the quality, that help you to find S3, which is equal to S4. Okay, so B2 equal to B3. Okay, I will use, okay, I will go to table, I want to check first if state 3 is superheated or not. Okay, so I want to check. So let's check using table A12, that pressure table. You check with the pressure table. Okay, so A12 pressure table, because we have the pressure. If we don't have the pressure, so let's we will see other things. Okay, so let's go to table A12. At the pressure B2 equal to B3. So at B2 equal to B3, which is 2000 kilopascal. Okay, why B2 equal to B3? Because I want to find H3, so at state 3 also. Okay, I want to check if it is superheated or not. Okay, and how can I check? I have the quality. So I have the entropy at S3. So let's see and go to 2000 kilopascal here and check if my entropy is lower or less than SG or higher. If it is higher, it will be superheated. If it is lower, it will be a mixture. Okay, if it is higher, if it is lower than SG, if it is lower than SG and higher than SF, it will be a mixture. Okay, so let's see. My S3 is what is equal to S4, which is equal to 0.8788. 0.8788 is less than 0.90184, less than SG, so it is a mixture. Okay, so as you can see, it is a mixture, means that state 3 is not here, it is not here, it is here. Okay, so and we predicted this because or we didn't predict this because we didn't find the quality, but the S3 was less than SG. Okay, so state 3 is here. Okay, so SF is less than S3 and S3 is less than SG. 0.8788 is less than SG and at 2000 kilopascal, which is 0.90184. Okay, SF is 0.52509. Okay, so it is a mixture. State 3 is a mixture. So always when you have a mixture, what we do, you find the quality. Okay, so quality X3 is equal to S3 minus SF over SG minus SF. and then I can find the quality and then use the equation again for the enthalpy. I can say that H3 also is equal to H3 minus HF over HD minus HF. Okay. Of course, at which state? At the pressure, or at which pressure? At pressure B2 equal to B3, because I am calculating for H3 2000 kilopascal. Okay, so X3 is equal to S3 is given the or we calculated X3 0.8788, SF is 0.52509 over SG 0.90184 minus SF 0.52509, and I want to find H3. HF and HG also from B2 equal to B3 2000 kilopascal. So these numbers HF 151.76 and 281.09. So let's write them. 151.76. HG is 280.09 minus 151.76. So the quality will be 0.939. Okay. So it is a little bit higher than X4. X4 was 0.93 only. Okay. And H3 will be 272.24 kilojoule per kilogram. Okay. So that is H3. Okay, what about the temperature? Now, if I draw, I know the real TS diagram for this cycle or this question. Okay, so let's draw it. Still, we didn't find anything. We won't find the temperature at state 3. Okay. So this is the TS diagram. Okay, we know that the pump we start at HF. We don't have subcooling. Okay, H1 equal to HF, and we go up to state 2, and we'll go like this, and then we'll go to the right, and we will not go until we reach the saturated vapor, because we have X3 is equal to 0.939. So it is something here. Okay. And we will go down. It is we'll go down in isotropic expansion process until we reach the condenser. Then we will go again in a closed cycle to state 1. So we have here 1, 2, 3, and 4. Okay, let's remove this one like this, because X4 is about 0.93, so it is better to draw it near state 4. Okay, so it is like this, the cycle, and as you can see that T2 is equal to T3. It is equal to these temperatures. They are at the same line. Okay, so they have the same temperature. So we can say that T2 also in this question is equal to T3, and this temperature is the saturation temperature. Okay, because it is inside the dome, it is a constant line, so it is equal to the saturation temperature because it is in the saturation region in the mixture. Okay, so it is equal to Tsat. Tsat at which pressure? At the pressure B2 equal to B3, which is what? Which is was 2000 kilopascal or 2 megapascal, right? So at 2000 kilopascal, 2000 kilopascal. Okay, at 2000 kilopascal. So T3 is equal to Tsat at 2000 kilopascal. So at 2000 kilopascal, T3 is what? Is equal to Tsat, which is 67.45. So now I find the first requirement, which is T3, and it is equal to 67.45 degrees Celsius. Okay, and as you can see, it is يعني it is better for us if we have reheating, not reheating, superheating. Reheating is other thing. We will have a cycle about reheating in the Rankine cycle. We have superheating if we have superheating, because this area is like this, right? It's like this shape. But if we have superheating, it will be like this shape, and we'll move a little bit further here to reach the saturation vapor line, and we'll go up with superheating, and then we will go down. Okay, and as you can see, this area, and or maybe a little bit, we take a region from here. Okay, this area is higher or bigger than this area. Okay, the total area for this one is higher than this one, and this means that we lost some work because we didn't do superheating. Okay, so that is it. Okay, and if you compare to the Carnot cycle, the Carnot cycle has this shape. If we draw the TS diagram, okay, for this cycle it will be like this, a square. Okay, so the good thing that we moved this point to be here like this, تمام. But even we didn't change anything here. Okay, maybe this one touches the saturated vapor, but this one do not touch. Okay, so the improvement for this Rankine cycle was this part. Okay, that we moved this point from here to here. Okay, so that is the difference. Okay, now we calculated every enthalpy, so and we calculated T3. The second thing that was required from us was the thermal efficiency. Thermal efficiency for Rankine, okay, you saw from the previous equation that previous question that it is H1 minus H4 minus H1 over H3 minus H2. Okay. So let's substitute in this equation. Rankine equal to 1 minus 251.16 minus H1 84.98. Okay, over H3 272.24 minus 86.1. This will give you that the efficiency is so low, 0.107. And it's equal to 10.7%. And as you can see, it is expected that it is didn't superheat, didn't reach even to the saturated vapor. But for this cycle, yes, we know it is the thermal efficiency is low, it is bad, but is it can we do a higher value, or what is the maximum value that we can reach? The maximum value we can reach for thermal efficiency for this cycle, that we have the thermal efficiency for the Carnot cycle, right? The theoretical efficiency for the Carnot cycle, which was the equation for this cycle, for the Carnot cycle, is equal to what? 1 minus TL over TH. TL the lowest temperature and TH is the highest temperature. The lowest temperature is what? Is given in the question, which is T1 equal to T4, which is what? 24 degrees Celsius, given the question. And we add the 273 to be in Kelvin. And TH is what? TH is this temperature. T3 we calculated here 67.45. So this one is 67.45, and we will add 273, and this will give you 0.1276 or 12.76%. And as you can see, our Rankine cycle, it's not that far, or it is so near, a little bit closer to the thermal efficiency of Carnot, and that is a good thing for us. Okay, but at the end, the cycle itself has a low thermal efficiency. Okay, I want to show you this because there is another question. I think this one, not this one. about this to compare between the Rankine cycle and Carnot cycle. Here in this question, and comparing Carnot cycle and between Carnot cycle and Rankine cycle, and he will do the same. Okay, so this question, what was this question? 24. Okay, so in the question 24, he drew the cycle and it was a saturated vapor. Okay, and he drew also the Carnot cycle, and he calculated the thermal efficiency for Carnot. It was 34%, and he used this equation 1 Q out minus Q in. But if you use also 1 TL minus TH for this equation question will be T3, and TL you can get it from here H1, and you will get the same number, 34%. So if he asks you about to compare about Carnot cycle and give an explanation or a comparison, you can write for this that Rankine we improved this because or remove the point because the pump will be affected by the vapor. Here if it is in Carnot is not practical. Okay, and as you can see, the efficiency for the Carnot is near to the for the Rankine is near to the Carnot, but the Carnot is the maximum one. Okay, that is it for this question. We still need to find the backwork ratio. Okay, the backwork ratio is equal to work pump in minus work turbine out. Okay, so H2 minus H1, our work pump in, we calculated work pump in, it was 1.118, but we didn't calculate work turbine out. But in the equation, as you can see, no need to find the work turbine out like this, from the equation. You can use directly the enthalpies. You find all the enthalpies, so H3 minus H4. Okay, so I will write H3 minus H4. Okay, and this one is already H2 minus H1, which is the work pump, so 1.118 over H3 minus H4. Okay, H3 is 272.24 and H4 is 251.16, and this will give you that back ratio is 0.053, and that is good because that means that the work pump is so small. Okay, because if it is so small or has a small value, the backwork ratio will have also has a small value. Okay, that was this question. We still have the last question in this video, and we will finish the question about the ideal Rankine cycle. And then in the next video, we'll talk about the actual Rankine cycle, inshallah. So let's see this video. Question 1014. We have a simple ideal Rankine cycle. Okay, we have ideal Rankine cycle which uses water as the working fluid. So let's change the color. Which uses water as the working fluid. So we return back to the water. So from table A4 to A6. Okay, operates its condenser at 40 degrees Celsius. So its condenser means this states from 4 to 1. Okay, so T4 which is equal to T1, which is here also equal to T set, because I cannot see in the question anything about subcooling. So equal to T set equal to 40 degrees Celsius. Okay, and its boiler at 300 degrees Celsius. The boiler 300 degrees Celsius means which one? He didn't say 2 or 3. In the previous question, we predicted that T3 equal to T2, or we know that T3 equal to T2 because we calculated the quality and we knew that the state 3 is here and it is mixture and they are on the same line. But here he didn't mention which one for the boiler. It is T2 or T3. It is T3. How you can know it is T3? First thing that T2 is here. Of course, it's not. He will not say 40, which is this one at state 1, 40, and then this one is 300. Okay. Of course, there will be a different. So T3. Okay, it is reasonable if it is 300 degrees Celsius. The second thing that he will never give you T2, because if he give you T2, if it is a possibility to give you T2, I don't know the reason, but I think that you cannot find the enthalpy at state 2 because you will not have numbers at this temperature, this state 2, because it's subcooled. I don't know, but usually he will not give you T2, and that is why we use this equation to find H2. We didn't use temperature on anything, so that's why H2 is calculated from other things, okay, from this equation. We didn't use the table for H2, so you are predicting it is H3 T3. He will not give you T2, okay. So 300 degrees Celsius is T3, okay. Calculate the work producing produced by the turbine. Even if it didn't say turbine, he will say work produced, okay. You will predict this turbine. So work out from the turbine. You want to find the work out from the turbine. The heat supplied in the boiler, so Qn, because the heat is supplied in the boiler, as you can see here, Qn. So Qn from T2 to 3, Qn is here, okay. And then the thermal efficiency, okay, the thermal efficiency of this cycle. And we said always, when you say thermal efficiency, means calculate everything, H1, H2, H3, and H4, okay. Of this cycle, when the steam enters the turbine without any superheating, okay, without any superheating, that means that if it is without any superheating, where is the superheating? Superheating is here, right? Okay, superheating is here, and then without any superheating, so we remove this part, so we are here. So that is T3, and now we can say that T3 is also equal to T2. Okay, so T3 is also equal to T2. Oh no, it's not equal to T2, and that is a problem. Was in the previous question I said it is equal to T2. I assume T2 above or here. No, this one is not T2. Okay, this one is state 2. Okay, that is a mistake. Okay, you can say that it is equal to T2. That is wrong. It's only T3. Okay, T3 is equal to T set. Okay, that is wrong, not T2 here. T2 is here. Okay, that is okay. It is a good thing to know that this point here as the saturated vapor, we don't call it any state, or don't give it a number. Okay, so not T2. Alhamdulillah, we saw this mistake. We realized this mistake. Okay, so it is not equal to T2. So T3 is equal to 300 degrees Celsius. Okay, so you want to find everything. Okay, now I am giving two temperatures. I don't have any pressure, so I will use the green. Okay, so for the green, T1 equal to T4. I have T1 equal to T4. I can find V1 equal to Vf, and V1 equal to V4, which is equal to B sat, and H1 equal to HF from table A4 at T1 equal to T4 equal to T sat. Okay, so let's go to table A4. Table A4. Table A4. At 40 degrees Celsius. Okay, and find Vf and also HF, and B set is equal to B1 equal to B4 at the temperature at this temperature T4. Okay, so now the TS diagram is like this. Will go down. Okay, so this region is cancelled, and state 4 is here. Okay, so to calculate V1 equal to Vf at the saturation temperature of T1 equal to T4 equal to 40 degrees Celsius, and it's equal to 0.001008 meter cubed per kilogram, and H1 is equal to HF, and also is equal to T1 equal to T4 equal to 40 degrees Celsius. So HF is equal to 167.53 kilojoule per kilogram. Okay, so P1 is equal to P4 equal to B sat, and this is equal to B sat at 40 degrees Celsius, and it is equal to 7.3851 kilopascal. Okay, now I can find the work pump in. You don't need to find work pump in, but let's find it. We will not lose anything. Okay, so work pump in is V1 P2 minus P1. Okay, B2 we didn't find B2 and it's not given the question, so we need to find it. Also, it will be the saturation pressure at T3. Okay, because P2 is what? P2 is equal to B3 at T3, which is equal to 300 degrees Celsius. It is the B set at T3 equal to 300 degrees Celsius. Okay, so 300 degrees Celsius here, B2 equal to B3 equal to B set equal to 8587.9 kilopascal. So this one is equal to 8587.9 kilopascal. So the work pump in is equal to V1 is what? V1 is 0.001008. B2 is 8587.9 minus P1. P1 is 7.3851. So work pump in is equal to what? Is equal to 8.65 kilojoule per kilogram. And then I can find H2. So H2 is equal to H1 plus V1 P2 minus P1. H1 is 167.53. We got it from the table, and V1 is 8. V1 B2 minus P1, which is work pump in, is 8.65. So this will give you 176.18 kilojoule per kilogram, and as you can see, it is a little bit has a higher value than H1, and the work pump in is very small, 8.65. So now we found H2. What about H3? H3 is saturated vapor. So H3, C3 is saturated vapor. So H3 is equal to Hg. So we have this case. Okay, H3 is equal to Hg and S3 is equal to Hg. I will not use the pressure. I have the temperature. Okay, the quality of course is 1. So it is a saturated vapor. So let's go to table, the same table A4, but at the temperature 300 degrees Celsius, and find what? And find Hg and Sg. Okay, they are equal to H3 and S3. Okay, so H3 is equal to Hg at 300 degrees Celsius, and this will equal to 2749.6 kilojoule per kilogram, and S3 is equal to Sg at 300 degrees Celsius, and this will give you 5.7059 kilojoule per kilogram. Okay, so and now S3 is equal to S4 because it is isotropic expansion, right? The entropy is the same. S3 is equal to S4. Okay, S3 is equal to S4. So this one is also equal to S4. And now I can find what? I can find the quality, right? Because I want the quality to find, to know how can I find H4? Is it from this equation, or it is equal to 1? That will not happen, or maybe 100%. And if it is a superheated state, state 4. Okay, so X4 is equal to S4 minus SF over SFG, which is SG minus SF, at where we have state 4, so at T4. T4, which is equal to T1, is equal to 40 degrees Celsius. So X4 is equal to S4, is this one, 5.7059. SF and SFG at this temperature, so at 40 degrees Celsius, 40 degrees Celsius, SF is this number, and SFG is this number, 7.6832. Okay, so SF is what? SF is 0.5724 and SFG is 7.6832, and this will give you that X4 is 0.6681, and that is bad because usually you want the quality for the turbine, for the outlet of the turbine, to be above 0.9, because the droplet of the liquid, if you have water, this will affect the blades of the turbines, شفرات التربين. Okay, so we want it to be dry, and we don't want that to have water. Okay, so X4, that's a bad number, but that's what we have in the question. Okay, who cares? So let's find H4, because the quality is less than 1, so I can use the equation for H4 equal to HF plus X4 HFG. Also HF and HFG is at state or at the temperature T4 equal to T1 and equal to 40 degrees Celsius. We are calculating for 1, so we will use the temperature 4. We're calculating for 4, so we're using temperature 4. Okay. So also at the same temperature T equal to 40 degrees Celsius, we will calculate what? HF and HFG. Okay, or we will find HF and HFG. So H4 is equal to HF. HF is 167.53, and this one is H1. We calculated also H1 at the same temperature, which was HF, so same number. X4 is 0.6681. HFG is what? I don't like to try this one. Estimate quality. So this one is 2406. So H4 is equal to 1774.98 kilojoule per kilogram. And now we found all of the enthalpies, so we can find the efficiency. Efficiency is what? Is work net, W small, this one is small, kilojoule per kilogram. Okay, over Qn. Okay, work net is what? Work turbine out minus work pump in. We calculated work pump in, but we didn't calculate work turbine out, so we will calculate it over what? Over Qn. Okay, or you can use the equation that H1 minus H2 or 1 minus this equation, H4 minus H1 over H3 minus H2. Okay, so let's try this equation this time. Okay, and find work turbine. Work turbine out is equal to what? H3 minus H4. So it is equal to 2749.6. 2749.6. Right? Why is this one is 1? It is not 1. It is. This one is what? H4. 1.77. So is this right number? Let's wait. Let's see. Let's calculate it using the calculator. 167.53 plus 0.6681 times 2406. This will give you, yes, this right. Okay, sorry, this one is H3. Okay, so this is H4. Okay, that makes sense. H4 1774.98. Okay, and this will give you that the work turbine out is equal to 974.62 kilojoule per kilogram. Okay, so Now I can use this equation, but still I didn't find Qn. So Qn is what? Qn is H3 minus H2. Okay, the right minus the left. Okay, H3 is 2749.6 minus H2 176.18, and this will give you that Qn is equal to 2573.42 kilojoule per kilogram. Okay, so the thermal efficiency finally it is 974.62 minus 8.65, which is the work pump in, over Qn 2573.42, and this will give you 0.375 or 37.5%. And now we finished this video. Inshallah, Rankine cycle or this chapter is the easiest chapter that you will have in thermodynamics, advanced thermodynamics. So يعني it is a question that you will get فيه mark, يعني you get mark in it inshallah. So thank you.